Let's start. So again, what we have in this slide that I added to slide set number 4 is give about the minimum reinforcement needed for beams. As we said, for foundation doesn't apply, for slabs this doesn't apply, for walls it doesn't apply.
Professor, is this formula more in depth of one-way action and two-way action, or no?
This is not for slabs. In slabs we say one-way action, two-way action.
Oh, okay. So
But
that's the
this doesn't
differential.
apply for all
Mhm.
slabs. So I'm going to
Mhm.
say here, any type of slab. I'm going to say no. One way, two-way slab, don't use this equation. This equation only for beams and girders. So as it says here, beams. You put this box here. So this only for beams. So as I was saying, if you apply the first condition, because you have here two minimums, one of them says it's going to be 1 square inch, other one says 2 square inches. Let's give you your option here. Of course, you need to satisfy this, the 2 square inches. But usually you have the required reinforcement, and then you have the provided reinforcement. We understand this. So if I go back here to this problem, is 2 number 8 and 1 number 9 is the provided or the required, according to your understanding? Let's see.
Provided.
This is one here is going to be the provided. So how much is needed? Based on this information here, can you figure out how much is needed as a moment demand? You can say no. If I need to calculate out, I need to have the load combinations, figure out the maximum demand. Maximum demand is the moment that you want this beam to support. And based on this, you can figure out how much reinforcement you need. And in this case, the other reinforcement that I was just talking about is going to become the required. So here, this is going to be the required. So what's provided? The one that you see in the beam. Your choice is going to be the provided. Now the code here says, if whatever that you provide is more than 4/3, like 1.33 times A required, you don't really need to apply this minimums. So in some beams, you see that the beam does not satisfy the requirement for the minimum just because the amount of load that you apply to it is going to be very small. And the beam in size just happened to be big because maybe you need for artificial reason. So in this case, you don't really need to put lots of reinforcing. You can just put whatever is enough, and then you add 30% on the top of it. Whatever is enough is AS required. You add 30%, you make it 1.33, and for that, this is going to be the provider reinforcing. And with that, you're good. You don't really need to provide the minimum. This minimum sometimes going to be too much when the beam is just large in size. I'd like to see if this is really the minimum in the same example that I have used. So this example, this slide here, it shows the same example in this slide set. Same one, 2 number 8, 1 number 9. If I go back here, let's say to slide number 2, this is the exact problem here. So I'm gonna go here to 8. It says here, check the minimum flexure steer ratio. Flexure means longitudinal steer ratio, which means the tension rebars in the beam. I'd like to check this against the minimum, but I don't have the demand. Let me go back here one slide. Why the demand? Because I don't have this required. So this entire condition, I cannot figure it out. Why? Because simply, I don't know exactly how much is required. All what I know, this is what was provided. I need to check this against the minimum. So I cannot use this exemption in this case. How do you check the minimum flexure steer ratio? I'm gonna go here, two equations. First one, it says 3 square root of F prime C. Of course, this needs to be in PSI. I cannot use it as in KSI. Okay? Divided by F sub y is gonna be also in PSI. Times the width is gonna be 16 by the depth. Your depth here is 30 minus 3 is gonna be 27 inches. It says here 16 by 27. My minimum steer ratio based on the first equation is 1.18 square inches. I said, okay, this is good. Let me try here the second equation. Second equation says 200 divided by F sub y, and your F sub y here is the 60,000. 16 times 27 is gonna be 1.44. Now, which one controls my design? I have two minimums. It's gonna be the larger of the two. You see, this here is gonna be my AS minimum. All right. What is provided? You see, what's provided is 2 number 8 plus 1 number 9. 2 times 0.79 plus 1 square inch is going to be 258. More than AS minimum, this is good. So now I check the minimum steer ratio for the beam in this case. Any question on this?
Yeah, so there's 3 in total, but 2 were number 8s and the middle one could have been a number 9 or
Yeah, this is here 2 number 8 and the middle is number 9.
Okay.
Usually you try to have some symmetry. When you do any beam, you try to have some symmetry here. So I wouldn't do number 9, number 8, number 8. I would do 1 number 8, 1 number 8, 1 number 9. It's
Okay.
not common. It is not common in practice. So if I'm doing here this for practice, I may add maybe 2 number 9 at the edge and maybe 1 number 6 if I'd like to reduce the amount of reinforcing a little bit. But in most cases, we try to make all the bar size to be the same in the same beam. So are we good about this? Check on minimum reinforcement ratio. It's your chance to ask me. All right. Now, let's say, same example, but see what's new. It says, check the minimum flexure steer ratio, provided that the design ultimate moment, M sub U, is 125 kPa per foot. Oh, now I have the demand. Now let me check this out. I'm gonna say the moment capacity is 291. You guys know where this comes from? The slide here, number 11, the last one. Let me go back. Original problem, the slide said. Here is Feynman. It says Feynman 291 kfoot, right? You guys follow me? 291 is the capacity of this section, this problem here. So what's happening here? Your demand is 125. What is the ratio between the provided to the required, in your opinion? You can say the ratio could be like 291 divided by 125. This is going to be here capacity to demand ratio, right? It's going to be 2.33. You see this 291, you have capacity of nearly 300. And your demand is 125. So actually you provide lots of steel, lots of capacity, much more than 1 1/3 of the demand. So in this case, I'm going to say, I don't really need to apply this AS minimum. I don't need it. No need to do the check. Why? Because the ratio between Feynman to M sub U is more than 1.33. Let me go back here. But here it says AS provided, doesn't say ratio between the moment to moment. It says ratio between the steel to steel. I'm going to say, yeah. But guess what? This AS provided is related to Feynman. Kind of a linear relationship. And AS required is also related to M sub U, the demand. And also you have kind of linear relationship. So when you compare the moment to the moment, it's going to be very similar to if you compare AS provided to AS required. Any questions before I move forward to the column slide set? Yes or no?
Nope.
All right, great. You save this. And yes.
For designing purpose, what should we actually, is that we want to, let's say, design a beam in a tension control area, then we actually figure it out the amount of steel we needed? Is it that way?
What you're saying is you'd like to have the beam to be tension controlled. Yes, this is one of your targets. Yes, this is true. One of your targets is to have the tension control.
Actually, a very initial assumption we do for designing is going to be that we want a beam that's going to be in tension controlled area.
This is correct. You'd like it to be in tension controlled area.
So what are the factors before we design? We need to define to just get to the size of the beam we want in design.
What are the factors?
Yes.
Factors can be the demand that you have in your beam, how much moment you want to support.
Okay, that's
how much shear,
actually
like the
that's
forces.
That's the known item, huh?
That's what?
Those are the known factors, I think.
Yes, the normal
I'm
factor.
talking about what we have. We have known factor. Okay, we know what strength we want, or compressive strength, I mean, and whatever those things. But is that I'm talking about the unknown parameters that we wanted to design for.
Okay, in your design, you have a capacity and you have demand, correct?
Yes.
All right. So your target here is to put higher capacity than the demand.
Yeah.
Makes sense, right?
Sure.
This capacity here is controlled by AS, the amount of cement that you put there, which means concrete strength, the concrete mix design available to you at this location. So you don't want to go with very high strength if it is unavailable. And the appropriate type of cement that you like to go and use it. So F prime C here is gonna be a major issue if you're doing an actual design. So you need to be careful about what is available, what's the cheapest option, and which one that needs a special inspection versus no inspection at all, right? So you need to be aware of all of that. In terms of performance, you need to be aware of if it's gonna be like flexure failure versus brittle failure. If it's gonna be tension control, it's gonna be ductile failure. If you have lots of reinforcing, it's gonna be brittle failure, compression control failure. You don't wanna go there. This when it comes to gravity members.
Okay.
Okay.
So E sub T, no, epsilon sub T is going to be more than, based on that graph, is going to be more than 0.004 in order to be in that ductility.
The strain, you mean?
Yes.
The strain, yes, is 0.005, if I don't.
Is it
forget.
00? I've seen in the textbook that it's some places says 0.004.
There's something called test and the code, right?
Yeah.
Okay, great. So I'm talking about the code. If I may go back here again, no, I don't have it in the slide.
Yeah, what we have here is 005, but I've read somewhere that we could use, the minimum of that is going to be 0.004.
Okay, yeah, but the code says this, which means that if you're doing an actual design, you need to satisfy that.
Okay, so 005 is going to be what we're going to assume.
Yeah. Okay.
Thank you.
No problem. Just here a question now for the quiz that we are supposed to take. Are you guys ready for it? Conceptual questions.
Yes.
Yeah.
All right. So can you guys see it now under quizzes? There's something there, but you cannot take it. Am I correct?
I'm still pulling it up right now.
Until 4:55.
Yes, it's there.
Excellent. And also this is gonna be proctored, right?
Yes.
This Proctoria. So we'll test it. We'll have fun with it. I tested Proctoria yesterday. It works fine. Absolutely fine. So we're gonna be using it.
Professor, where can I find it? I can't seem to find it.
Under
Go to-
quizzes, you don't see it?
It's
Under
So
under.
quizzes?
I didn't find it when I went on home, but you can find it on the right in the to do.
Mhm.
You'll find it quiz 1.
It's also under assignments.
Yeah, it's upcoming assignments, quiz 1.
Yeah.
Oh, okay, I see it. Yeah, it's under assignments.
Comes two places usually. It comes in assignments and also is like here, if you guys can see it. Under assignments, also it comes in the quizzes. Also under quizzes, also I'm able to see it there.
So are we going to be in Proctorio and in Zoom at the same time?
Yeah. So on the quizzes, you're going to see it there. All right. It
So
should be simple. And
do
you're
we
going to
need-
be typing in. You're going to be typing
typing.
in on the screen. So on the screen itself, on the computer, you're going to be typing in. There is nothing here to upload.
Like basically problem 1 on their exam.
Exactly. And then after you're done, you're going to submit. It shouldn't be tough. And you don't really need 20 minutes because I'm sure that you guys should be able to do it in 10 minutes, but so that you have enough time. In columns. Now columns can be those vertical members, structural members supporting beams and slabs and whatever that you have on the top of it. We have gravity columns and seismic columns. Hey, Alex, you have an internet issue?
Since I'm going to be using Proctorio on my...
Okay. Yeah, you need to have Chrome, right?
Yeah,
Your
so
browser?
what I'll have is I'll use my main computer, my laptop that I'm using to take notes, and just
Okay.
type it in from there.
All right. So we have two types of columns here. We have gravity columns and seismic columns. So when it comes to lateral forces is resisted by moment frames or shear walls. We're not covering it in this course, but you need to know about it. So when you have this seismic moment frames, you're going to have columns and beams. So in here, we're going to be covering only gravity columns. So gravity columns, it's not going to be part of the moment frame system. And the forces going to be completely different. The forces that you're talking about here is going to be mainly axial load. So here we are talking about axial loaded columns. And sometimes we have also slight moment on the top of it. So you're going to have an axial load and some moment on the top of the column. Type of columns. We call this tied columns. So here's a column, concrete section, and then you're going to have ties. So this is the reason that we call it tied columns. And tied columns, if you look here at the elevation of the column, here's the vertical rebars or longitudinal rebars. And you have some ties. And here's a tie. It needs to enclose the entire, all the vertical rebars. The way you build it, you put the cage first, then you put it in the form, then you pour the concrete from the top. We have also spiral columns. So in the spiral column, is going to be most likely is going to be like round, but also you may have a spiral column, and the column itself is going to be rectangular section. So you can have a column like this. You do the form like this, but you have the rebars is going to be in this round shape, and the tie or the spiral, we call this a spiral now, we don't call it the tie, is going to be also in round shape. So in this case, I'd like to see here the big difference between the two. In here, if you look, I know that this is not to scale, but look here, the spacing between ties. It's kind of large when you compare between here, the spacing here between the spiral. We call this the pitch. Look also at this tie. Each one of this tie is going to be a separate piece. But here the spiral is what? It's like one piece. If you think about it, it's just one piece that goes around. So if the entire tie here, let's say that you cut one piece in here, you cut it in the middle, and then let's say that there's no concrete around it, you start to pull it from the bottom, you can just take it out. Because this is the whole thing, here's one piece. But here, it's going to be one separate piece at a time. We can have also these composite columns. Composite columns means that you have a steel section, like you have this pipe, and then you fill it in with concrete. Or you have this steel section, and then you encase it with some concrete. In this case, you have steel and concrete that they act together to support the column vertical axial load and the additional moment with it. Same thing here with the steel pipe. Now I'm thinking here, what is the need for the vertical rebars? These vertical rebars, they support also vertical load. So if this gonna be here, the vertical load, it's coming down. In this concrete section, it supports in this section here supports this vertical load, and also this 4 rebars, they support the vertical load. So the rebars and the concrete, now which rebars? I'm not talking about the ties. This vertical rebars, this 4 rebars, and the concrete, both of them as one element, one structural member that we call the column supports the vertical loads. Meaning this force here is going to split. One section of this force is going to be going to the concrete, and one section is going to be going to the reinforcing bars. In our design here, what we do, we say we'd like to be sure that phi Pn is going to be more than or equal to P sub E. Same equation like the moment demand, like the shear demand, but in this case, it's going to be axial load demand. Demand, we understand the demand. You're going to have the reaction from the column or on the column, and you can do the 1.2 dead load plus 1.6 live load compared to 1.4 dead load, and then you take the largest. With that, you have the demand. So demand is going to be based on the applied forces. Now look here for the strength. The strength is going to be combined action between the concrete and between the reinforcing bars, which means it's going to be somehow like in the shear design. If you guys recall, we have concrete strength, and then the rebar strength, and then we add them. It's going to be the same thing. We're going to have here the concrete strength in compression, and the vertical reinforcing bars also in compression, and then we add the effect. Okay, now I understand the purpose of the concrete or the significance of it, and the same thing for the reinforcing bars. I'm wondering what the ties going to be doing. Do we really need ties? And I'd like to hear from you guys, your input on the ties.
Actually, I think those ties is going to resist the lateral forces.
What lateral forces? I have just vertical force, right?
Like shear force? Oh.
Let's say in this columns, because only for gravity there is no shear forces. In seismic, it's true that you're going to have shear forces, but in this case, there is no shear forces. Any other idea? Thinking about this?
Maybe just to help not buckling.
Exactly, what is not to buckle?
Actually, the stem of the column, probably.
Stem or this vertical rebars. If you don't have these ties, and all of a sudden now you start to apply the vertical load, what's going to happen to this vertical rebar? Vertical rebars wants to do this, right? Correct?
Yes.
Wants to come out. And actually, the entire section of concrete, if you start to apply forces, vertical forces, you're going to see here some lateral forces, right?
Actually,
it wants to open up.
Those going to actually act as a support for mid-span or whatever.
For the vertical ties. For the vertical rebars. So once you start to apply here a vertical load, this column wants to open up. And all of a sudden, if you don't have any of these ties, you're going to see a vertical crack, right? Now, what is bringing the rebars together and putting all of this concrete together is give you the ties. This is why in column design, the code requires certain spacing of the ties and certain size of the tie itself. So you cannot just go with any tie spacing and any tie size. You need to satisfy certain requirements. We call this also confinement because this ties here to provide confinement for the concrete. So if you think about taking, let's say, concrete sample or a cylinder, here's a concrete cylinder, right? No reinforcing. This is the section through it. Put it under testing. And then you bring another concrete cylinder, and then you put some spiral like this. Which one do you think is going to be stronger? We're going to say, well, I understand that the mode of failure is going to be opening right in the middle. We're going to be like a vertical crack. I understand that. And having all of the spirals, all ties, is going to keep the concrete all together inside this shape. Therefore, this confinement provided by this tie is going to increase the strength of the concrete. You can see, yeah, this is true. Confinement here is going to be very critical. Now, I want you here to think about the concrete that you put inside the pipe. This is going to be like fully confined because all the entire concrete is contained. Now put pressure on the concrete here. How do you think about the strength of it compared to this, compared to no reinforcing at all? you're gonna see the strength is gonna be extremely high because the concrete doesn't have a place to go. If you want to fail this section here, you need to fail this concrete, this steel shell first. It's gonna take lots of vertical force because the horizontal force here is gonna be a fraction of the vertical force. You guys remember Poisson's ratio or Euler equation for buckling? This is gonna be the one that governs the amount of force that we're talking about. Now I'd like to compare between tight columns and spiral columns. Which one do you think is gonna be stronger? If you have the same cross-section area, if you have the same vertical reinforcing, but here you have more spiral because look at the spacing here. It's gonna be very tight, right? So which one do you think is gonna be stronger? Is it gonna be the tight column or the spiral column?
Spiral.
The spiral is gonna be stronger, and we have our reason. We have more confinement. Concrete properties is gonna be much higher. Performance is gonna be much higher in the spiral columns. Some pictures here. Yeah.
For spirals, would it cost more, correct?
Yeah. Sometimes it depends
Mhm.
because the way that they build it, they can have just the spiral. They put in the machine. It's gonna do it for you. It's not gonna be handmade, right? And once they put it there, they put the vertical rebars, and then they put the spiral. It's gonna be kind of shrink. It's gonna be at the bottom. They start to open it up and then put the ties. There's some ties, you know, the tie wire. They're gonna put it there.
Does it also require less like concrete, less material, or is it
No,
about
no, the
same?
concrete material is gonna be whatever that your section that you want it to be.
Okay.
Yeah. Here's some tight columns, and you see the way it is built. And then on the top, you're gonna have some dowels that sticks above, and then you see that they bend it inside because a new column is gonna come on the top, and the rebars needs to overlap with this dowels, like what you see here. The spiral column, like here, like usually is gonna be for bridges and big holes. You're not gonna do it on an office building, but most likely if you have a parking structure, or like in a bridge. And in most cases, you can just build this on the side and then just carry it with a big crane and put it in place, put the formwork, and then cast it. And again, you're gonna have some dowels stick above, right? Here's what happened. Here is the load versus the strain for columns. You apply some load, you get some strain or deformation, vertical deformation. And look here, for a spiral column, tight columns, at the beginning, they're gonna be acting the same. Till you get to a point. After that, the tie itself is gonna start to open and the spiral is gonna be continuous. Let me explain this to you a little bit here. You see here, the closure of the tie. If you apply very high vertical load, at certain point, this leg is gonna start to open. Instead of having it this way, the leg, instead of coming this way, is gonna open like this. It is gonna open like this, right? And then you're gonna see that the tie here start to open up. You don't have this situation here because when you apply high load, there is no place for this to go. The tie is just continuous, or this spiral is continuous. It doesn't stop. This is why the performance of a spiral section will continue here. But in this case, the tie is gonna start to open and the concrete is gonna start to fail in compression. In this case, here's the spiral is gonna continue a little bit more. The code recognizes this issue when it comes to the equation. Look at this, the phi factor. You remember that in this phi factor or phi chart, we have one chart for the spiral. We say this gave you mostly for columns, right? And this spiral here, the others, we said that this gave you for beams, right? Or tight columns. So if you have tight column, it's gonna be here. If you have a spiral, it's gonna be here. So the first issue, if you have a spiral column, your phi factor now becomes 0.75. If you have tight column, the phi factor is gonna be 0.65. You're not gonna be doing this straining the steel because strain the steel here is not gonna be in tension. It's gonna be all in compression, which means that you're gonna be in this side of the chart. So this phi factor 0.75 would apply for the spiral columns, and this phi factor of 0.65 is gonna be for tight columns.
Professor,
Yes.
the tension control, that's where you pre-stress some rebar while it's being cast in place, correct or no?
No, it is not related to this issue. The pre-stress different different issue completely. Yeah,
Okay.
yeah. But thanks to bring this up. So as I was saying here, if you have a spiral column, you're going to be using phi factor 0.75. If you have tight columns, it's going to be 0.65. Now we understand the reason that we have this dashed line. For tight columns, the equation is very simple. Look at the equation here. This equation I can split in two pieces just to make it simple. It's going to be the first term. It's going to be the second term. This first term is going to be for the concrete strength. The second term is going to be the steel strength. So this here is going to be for the steel. It says F sub y times AST. What is AST? Cross-section steel area for all the rebars, vertical rebars only, not the ties in the column. How about this section here, or this term? This is going to be the concrete. Like, you know, in concrete strength, we would say 0.85 times F prime C times AC, correct? Concrete area. In this case, we say gross area of the column, subtracting the steel area. I'm going to go back here a few slides. I'm going to be looking at this. I'm going to say, which means that you need to find out the cross-section area of this column, subtracting this whole rebars out of it to find out the net concrete area, if you like. Let me move forward to my equation. So, okay, how about the phi factor? How much is my phi factor? In tight columns, we know it's going to be 0.65. So this equation is so simple. It's going to be the compression in the concrete and the compression in the steel. And in this case, we say steel is going to be yielding and there's no other option. This is going to be it. Steel is yielding, there's no check on that. It's going to be yielding for the strength of the section in compression. There's no tension here. So as you see here, the equation is so simple. But when it comes to minimum and maximum steel ratio that you put on a column, code says your minimum steel ratio is going to be 0.01 times AG, which means it's going to be 1% of the cross-section area. And your maximum is going to be 8%. You cannot go beyond the 8%.
Professor, the right side of the first equation, the Fy area steel.
Yeah.
So that's, could you repeat what that all means in this equation?
This is here. This could be the steel contribution to the strength. So I'm going to say steel compression or compressive compression strength. You want it to fit, didn't fit. How about here? What is that term? Just give you the concrete. Compressive strength. Okay. So this section here is going to be the concrete, and this section is going to be the steel. So we say the steel is going to be yielding, right? There's no other option. You don't have to back check and find out the strain of the steel. This for the capacity point, concrete is going to be yielding, right? In compression. And here, this is going to be the concrete strength, 0.85 F prime C times the area of the concrete. Your phi factor is 0.65. Someone's going to say, how about this 0.8? Where it's coming from? You can say this 0.8. I will come to you, we'll discuss it. Please give me a second here. So we're back. Now the question here is going to be about 0.8, 0.08, excuse me, 0.8. And we'll be talking about this in details, but maybe next lecture. We're going to have another slide to show you why we have this 80% for reduction. The reason that we have this 80% is because there's going to be some eccentricity in the loading. Eccentricity meaning, if I may go back here, here's the column section. Axial load most likely is going to be right in the middle. So I'm going to say your axial load is going to be right here in the section, right? But in many cases, it's going to be eccentric like this, which means the point load is going to be like this, right? Compared to the section. So you're going to have here the vertical load, and then you're going to have this E, eccentricity. the distance from here to there, right? And this E is causing moment on the column. So this axial load multiplied by this E is giving you some additional moment. And as long as you have very small amount of moment, you call it small eccentricity. So as long as you're going to have this within this small eccentricity, your equation is still valid, and you don't really need to check the moment demand on the column. And instead, you just provide here 80%, which is reduction of the concrete column strength. So what is this 0.84? I'm going to say this gave you for a small eccentricity effect. You like this, right? Fine. Let's go here to the spacing. If you have a column, you need to have at least one vertical rebar at each corner. You cannot have one column and then you have the ties, and let's say this rebar is going to be missing. So minimum, according to the code, you're going to have one rebar at each corner. And you need to have tie that just contains everything in here. The spacing between two rebars is going to be 6 inches. Therefore, the spacing as it's shown here is going to be less than or equal to 6 inches. So maximum spacing between two vertical rebars is going to be 6 inches. Look at different configuration. In some cases, I need to provide this cross tie. Let's say that I have here 6 rebars, right? Then I need to provide this cross tie. Some cases I have here 8 rebars, just one tie, and then all of a sudden I start to add here cross ties. Well, it means that I need to do some analysis for the ties that you don't see here. So if you look here at this equation, nothing here, no discussion about how to do the tie analysis. The code here in California says these ties are mainly needed for seismic. But here I'm doing gravity column. But also for gravity column, there is some seismic requirements for it. Because here's what the code says. Imagine that you have your building, and your building is supported by laterally by moment frames, seismic moment frame. I understand that. And this seismic moment frames and this columns is going to be taking the seismic forces, lateral forces due to earthquake. But the problem here is going to be with this gravity column. This gravity column is going to be riding with you. I mean, it's true, when the building is going to be moving, all the columns are going to be moving with it. The column that you're supposed to resist these movements, and also the column that is just already there, but they have to move with the building. So you're kind of bending them. You apply here some moment to them. Whether you want it or you want them to resist it or not, you don't want these columns to be failing because the amount of cracking in there. So in California, seismic code, they have certain provision for gravity columns. And this going to be dedicate here the number of ties that you need to provide. Most likely, if you're in California, you don't do the column this way. It's going to be most likely like this. Because you need to have ties, enough ties in here. Or let's say if you have this number of vertical rebars, you're going to have this number of ties here, or this amount of ties. Look at the tie spacing. This now is going to be from a tie to a tie. Look at this. Code says the following. The maximum spacing here between two sets of ties, because look at this. Here's one tie and here's a cross tie. You see this cross tie? You see my hand? Here's the original tie, and this gives you the cross tie. Another cross tie from this side. Here's the tie, and this gives you the cross tie. This and this. What cross tie? This give you the same as this cross tie, like this guy here. This is what we call here cross tie. Cross tie. This give you the main tie.
Is it 6 inches on center or just at the
Yes.
rebar?
Yeah. So let's look here. This give you the main tie, right? And this give you cross tie. This give you the leg, and this is the hook of the other cross tie. The code says for gravity columns, and this is going to be general for all the states except for California. Or let me put it this way. As long as you're going to be in a low seismic zone, the spacing between the ties is going to be 48 times the pi biodiameter. So let's say here I put here half an inch. What's half an inch? Like number 4 is going to be half an inch. You say half an inch for the tie. Number 48 is going to be how much? 24 inches. So the spacing, the first check here that you need to do is going to give you here 24 inches. Or it's going to be 16 times the longitudinal bar diameter, the vertical bar diameter. Let's say here that goes number 8. So we're going to say 16 times 1 square inch for the diameter. It's going to be 16 inches. So the first condition here says 24 inch. Second one says 16. Now, which one here is going to be controlling? I'm going to say this one, of course. And this also says the least column dimension. So let's say the column is 24 by 24. Or the column, let's say, is 12 by 24. The smaller column dimension here is going to be 12 inches. Looking here at the 3 conditions, they're going to be taking the smallest of all of them. So in this case, it's going to be 12 inches. Now let me put it again. I'm assuming here that I have number 4 ties. Let's give you the given information. The column size, I'm going to say 12 inch by 24 inch. Vertical rebars, number 8 verticals. This is a given information, right? Now let's do here my analysis. According to item number A here, I'm going to say A says, I will have the spacing to be 48 times the tie biodiameter. So I'm going to say 48 times 0.5. Where does 0.5 come from? Number 4. It's going to be 24 inch. B is going to be 16 times 1. What is 1 for number 8? It's going to be how much here? 16 inch. Least column dimension. What is the least column dimension? I'm going to say here C is going to be 12 inch. Now, what is the maximum spacing that you provide here for the tie? I'm going to say in this case, give you the smaller of all of them. It's going to be 12 inch. But guess what? If you're in California, you have maximum of 6 inches because you have some seismic requirements for gravity column. Are we good? But this information is clear. And this is an actual column that I have taken here a picture of, right? Look at this spacing here. About 5 inches. Look from center to center. It's 4 inches. Look at this. Here's the half inch. Here's the half inch at 4.5, which means from the center to the center is going to be here how much? 4 inches. Look what the code says in a situation like this, 12 inch. But if you do it here in California, it's going to be 4 inches only. Ready for the quiz? Yes?
Sure.
All right.
Yes.
It's going to open up in half a minute from now. You guys let me know once it opens up. There's nothing to write, nothing to upload. You guys see it or no? Not yet.
Okay, it's open.
Okay, great. I guess here's the question, and give me please a minute or a moment. Just understand what's going on. Question about the typical unit weight. You need to put it there. So you have how many problems? 1, 2, 3, 4, 5, 6, 7. Just type them in here. At the end, you're going to submit, right? Any questions before you start? Yes?
Just still signing in.
Was this open notes?
You said it?
Yeah.
Thank you.
But finish it quick.